My name is Riccardo Grassa, and I am a computer scientist under INAF, the National Institute of Astrophysics, located in Italy at Padua. And this is my presentation titled Unifying Super Resolution and Object Detection, Advancing Lunar Remote Sensing with AI, with Artificial Intelligence. So today, we'll present an approach that tries to unify super resolution and object detection to try to enhance the remote sensing applications with a focus on planetary exploration, of course. This work is particularly relevant for crater detection and other geological structures on planetary science, on the planetary surface, where high resolution imaging is often a limiting factor because we get data from satellite data, of course. And I will begin with an overview of super resolution object detection. Then I discuss the integration and present our model for super resolution plus object detection. Finally, outline some results and applications. So what is the super resolution? It's a computational technique aimed at improving the resolution of an image or of a simple image by reconstructing the finer subtail and details from multiple or a single low quality images. So super resolution enhances the visual clarity to benefit in essential situations like, for example, the data get from satellite data. So instead of what is the object detection is a fundamental task in computer vision that it identifies and localizes object within an image, and it plays a crucial role in applications such as autonomous navigation, scene understanding, and planetary exploration in general. And the last part is the combined approach to demonstrate a key, or what I mean to say is the synergy between these two very big concepts. So, as I said before, the super resolution is a computational technique that try to reconstruct high resolution images starting to have a low resolution input. And this is especially useful in remote sensing and is very challenging due to the instrument limitation, for example, atmospheric conditions and or data transmission constraints. So mathematically, il super resolution aims to approximate the inverse mapping that you can see in the second equation in mathematical form. And by starting to have a degradation function that you can see in the first equation, the equation 1, which include downsampling and noise. So the traditional method, such as bicubic interpolation, bilinear, Lanczos filter, and so on, are limited, uncrafted assumptions, of course. So in contrast, deep learning-based approaches like convolutional neural network, CNN, and generator adversarial network, like, for example, the GAN, leverage hierarchical feature extraction and adversarial training to try to reconstruct final details as much as possible. However, the problem of super resolution is an ill-posed problem, because as multiple high-resolution images can correspond to the same low-resolution input. That means that the downsampling function is a surjective function, and the inverse function of the downsampling is again surjective function, but not injective. So this nature of not by action makes learning-based solution particularly important, and the process can accept different solution given a low-resolution image input. So an open question can be what could happen if we eliminate downsampling in the training process. That is a good thing to do. But to be more precise, in terms of mathematics, the model cannot generate all possible high-resolution images set from a low-resolution set. So because it depends by the training data distribution, by the capability of the model, by the capability of the design architecture inside the neural network. And so the goal, not the goal, the final thing is that with this formula is the function is not subjective, but in general we can say that we can imagine this in an ideal case, we can affirm that it is a subjective function. The last slide is a huge image about super resolution framework in a tiny nutshell. Everything known is described in the part of the resolution is described in this slide as a simple title. I cannot describe in this presentation, but it can be useful to show you the different network design well known in the literature. Where I also show a simple diagram of the network design below. So, for example, choosing a good network design, it's very important to generalize better the learning capability by a well-trained model. Like, for example, exists in the literature different technique like the residual learning, the recursive learning, dense connection, multi-branch network, dense in residual dense connection, that is like a combo strategy. And of course, we can have a lot of new improvement with the evolution, the next step of the convolution neural network, such as, for example, the transformers like the point C or what I mean to say is the channel attention that is very important, like, for example, the self-attention. And again, about the different learning strategies, we can have a family of many loss functions in always talking about the super resolution, of course, like, for example, the pixel loss, the context loss, the adversarial loss, and so on. Others notable things are integrated in the concept behind the data augmentation, such, for example, the blurring, the noising, the Poisson filters, the Gaussian noising filter, and the compression inside the how to get a good learning model using different kind of, or a combination of different kind of this type of data augmentation. But we can have also the mosaicing, the shuffle, the stretch, the flip, vertical, horizontal, and so on in the site of object detection, and but also in segmentation classification task. The performance metric are very important, as you can see on the left side on this image, because the metric are very important to evaluate the goodness of your trained model, and are reported in a simple PSNAR, SIM, the perceptual quality, and so on. And we can apply super resolution in many different domains, as intended as final application. For example, the depth map in super resolution, the phase image resolution, hyperspectral, multispectral, and so on in image resolution, real world, and so on. Let's go to the next slide, where I put a comparison I made by myself between two images of the moon at high resolution and the super resolution prediction on the right side. So high resolution is on the left side. As you can see in the bounding box, in the red bounding box in the right side, we show very high design, very high fine details. I mean, unveiling the power of the main approach and demonstrating the effectiveness of a well-trained model when we observe this kind of high-resolution images. The next step is the task of the object detection. That is a key task in the computer vision that involves identifying and localizing object inside within an image. And it can be seen as in essential tools in remote sensing, autonomous navigation, planet exploration, face recognition, and a lot of many applications. But more formally, let FD theta be a deep learning-based object detection parameterized by theta, where the theta are the parameter of the model, or if you want, you prefer instead use the word parameter, you can shows the word weight, the weight of the model, that map an input image I to a set of detected objects, where the set of the detected object are described by a triple offset, BI, CI, and CI from E equals to 1 to N, where BI belong to R4, representing the bounding box of the predicted location of the object itself, like for example the center X and Y, the width and the height of the bounding box. CI are represented the predicted class from the label C, the set of C, from 1 to C, to C, yes. And of course, if you have a data set composed by only one class, the set is composed by only one element, of course. And CI belonging to in a range 0 and 1 is the confidence score to establish by the model if the predicted bounding box is more or less confidence for the object detected. Is a simple scalar value. So the model parameters, the weight of the model theta, are optimized using an algorithm like, for example, the SGD, the stochastic gradient descent, that is in technical term called also the optimizer. That the goal of the optimizer is to try to find the global minima or a good approximation of it, like for example, one of the many local minima we can have, where in the surface that we can generate given the loss function we chose. So of course the gradients are computed via back propagation. In terms of object detection, we have two typical paradigms. The single-stage detectors, such for example, a well-known model like for example the YOLO, and which process an image in a single step, in one step, and then is very good for real-time performance. And the other kind of family is the two-stage detectors, like for example the fast RCNN and family, which refine the object proposal for improved accuracy. Below I showed an image which compare the two concepts inside the neural network model, where the only difference in the two-stage detectors is the refinement you can see in the sparse prediction title on the right side of this image, where the only difference is the refinement bounding box regressor strictly linked with the ROI, the region of interest. And this last part is responsible to refine the better and more discriminative features thanks to the classification layer and improve the main accuracy in the object detection task. But this is not a good approach for the real time detection, because it is more slow than the single stage detector, like for example the famous YOLO. So these models, this slide is intended as the characterization for loss function most used, and this model optimizes different loss function, not only one, including the classification locks, that you can find in a two-stage detector, the classical cross-entropy loss function. Instead of in the single stage, it's preferred to use the focal loss that is very useful for when we have a strong imbalance class about our data set. Then we have another type of loss function called bounding box regression loss, as for example the L1 or a simple Euclidean distance, or for example we can use the L2 and so on. And another one is the intersection union-based loss. And the last loss function well used is the objectness loss, that is a simple binary cross entropy, which emphasizes better the error in the presence of the object and doesn't learn anything about the background of the image. So a key challenge is that the classification accuracy and localization precision are not event independent. So that means that the optimizing one of these loss can have a negative impact in the other loss. So this is a corollary because we can observe continuously by experiment this kind of behavior. If you optimize one and so decrease the classification loss, it is possible that the regression loss doesn't benefit so much and can impact negatively for the learning, for the entire learning process. But however, in the second stage detector, I'm talking about the first single stage detector, but however, in the second stage detector, the regression box is improved thanks to the classification step. Using a small network, using the ROI approach, the region of interest approach, and so the features tend to be more discriminative using the single stage detector, thus bounding box, the regression of the bounding box law are improved. The classification loss is well optimized in conclusion in the second stage detector than using the one stage detector, and the regression loss is less than the equation one due to this a simple trick. So in conclusion, this is a straight corollary, but under certain conditions. It depends by our training, it depends by the model architecture, the parameters, and so on. But what I mean, that is important that this kind of event, this kind of probabilistic event are strictly dependent, not independent. So introduction, this is an introduction by the HoloLens. It's a model that combines like a hybrid approach between super resolution and object detection. Is particularly relevant for the planetary science. This is a model, I built this model 2 years ago. And the goal is starting to have a low quality data. The goal is to improve the resolution by a factor by 2 times of this the input source, and then we can extract a lot of main information like detection using a single stage detector, like for example YOLO, in a unique end-to-end model. So by incorporating a super resolution, we enhance the quality before the detection, allowing the object detection to extract more meaningful features. This approach benefits applications such, for example, the crater detection to detect the pit and cones identification or the volcanic structure mapping and so on. And in fact, our proposed model, HoloLens, integrate both super resolution model and YOLO-based object detection in a single pipeline, in a single end-to-end model. So the super resolution component reconstruct the final details, and while the object detection component leverage this enhancement for improved detection performance. So HoloLens is designed to improve object detection and in remote sensor application, challenging different kind of by addressing key challenges such as low resolution and noise. So the key features of HoloLens are the improved details capture, the super resolution module enhance fine-grained details, aiding the object detection process, end-to-end integration. The model processes images in a single pipeline, in a single end-to-end model, as I said before, reducing the computation overhead and improving efficiency. And we can try to find application over the planetary science. Our HoloLens is particularly suitable for crater detection, geological feature classification, where high resolution imagery is critical. These are a collection results of the paper I reported at below. The effectiveness of the super resolution plus object detection model is demonstrated in the first two images on the right side, where we compare the error in the predicted craters diameter between the classical YOLO baseline, left side, and HoloLens model, right side, in the right side of the image, and reported invariance percentage. Of course, close to 0 is better. In the second row, always in the right side, we report the better confidence achieved by super resolution plus object detection than YOLO baseline with the same training condition. Close to 0 is better again. The result suggests as a synergy between super resolution plus object detection to optimize the object detection task thanks to the super resolution task. Instead of on the left side, the first global AI lunar catalog entirely predicted by artificial intelligence. On the left side, and the manual validation of the model you can see on the left side, and plus the automatic validation across the Robbins well-known ground truth dataset used. And I invite you to check these two papers because we have the presentation of the model and the releasing of the first AI global lunar catalog about the craters. So this is a simple statistical analysis between our AI-derived catalog along others, across Robbins and Wang, and the size frequency distribution perfectly aligned with us, then Robbins, Neukum, Power Law, and Lefebvre, and so on. Of course, you can download the global catalog at Zenodo because this is available, and the sub-catalog using a base map of 21 meter pixel of Kaguya, where we report an incredible number of craters thanks to the high spatial resolution where we start. The last slide is this. Beyond the craters, we are extending our methodology to other planetary features, including volcanic structure, landslide, and pit and cones. We have also developed an enhancement object detection model that leverages multimodal data, allowing us to explore permanently shadowed region as much as possible, of course, in planetary environments. Our ongoing work involves integrating transformers with the convolution neural network to improve object detection in challenging scenarios. And in summary, our research demonstrated that integrating super resolution plus object detection significantly improved and enhances the planetary remote sensing in general. So HoloLens models like HoloLens provide a unified framework that improves the feature extraction, detection accuracy, and particularly for a small or low contrast object. This is the last slide. Thank you for your listening. And another thing that is an important thing, I suppose, that I invite you to check our upcoming special issue on advancement in deep learning for remote sensing, the Remote Sensing Journal, that the goal is bringing together cutting-edge research at like it was the intersection of deep learning and remote sensing. And the special issue aims to foster interdisciplinary collaboration And we encourage your contribution that not only push into methodological boundaries, but also offer practical insight for real-world application, like, for example, the remote sensing data in the space science. Thank you.